Okay, I would like to start with just a small review, just to make sure that we are on the same page. The task for divergence, okay, is really important. Okay, at the first uh, introduction in the series, that means that if the series is convergent, the limit is zero. Okay, that's for sure. The second theorem, if the limit doesn't exist, or if the limit is not zero, then the series for sure it will be divergent. Okay, and remember that we cannot reverse the first theorem. Okay, so if we say if limit zero, so if limit of the sequence is zero, the series convergent is not works that way. So we cannot work this irreversibly. So this is only work when the series is converged, then we are for sure the limit of the sequence is zero. And we've seen this in the 1 over n. Okay, we remember we have the 1 over n, and if we look at the sequence, so if we have a sequence 1 over n like that, if we take the sum of this will turns out to be diverged, right? So let's say this is divergent or diverge. Okay, and if we look the limit, this is zero, right? So it's not applied to this part of the problem. So if we reverse this statement, then it will be improper. Okay. Okay. Now we are going to look at the next sections, which is the test, the integration test. Okay. Let me move this to the new page. Okay. So let me write here integration or integral test. Okay. Okay, now if we take the sum of this 1 over n squared, so we have remember that on calculus 1, okay, we did the improper integral. If you remember, we did improper integral that is we did this two integral, right? One is converge, one is diverge. Okay, and you will see the similarity in the series. Okay? So if we have this series, so if we want to analyze the sequence that is 1 over n squared, and let's say we are going to take a few terms and see how it looks like. Okay, and then perhaps we can make some n. For example, we can try some n equal 5, n equal 10, or even n equal 100. And if you check, maybe using calculators, maybe using some computations, you will see that this will goes to a constant. This will goes to a constant. Okay. So we take the partial sums. Okay, we take the Sn. So Sn will approach a constant value. Okay, this is just from rough computations. You just trial and error. Just put some numbers, and it seems that it is going to have a constant value that is equal to approximately 1.64 something. Okay, this is the number. Okay, but what's interesting on this 1 over n squared, as we did in these integrations, because we know we can integrate this, and we know that in the previous calculus 1, we know that this will be convergent. So maybe we could make some approximations through those integration techniques. So let's say we are going to describe this, okay, in terms of area under curve. Okay. So of course we have this is the curve, okay, and you will see that at the beginning it has this, we say, is this whole, right? Not the area. The areas we approximate within this rectangle. And when you see this, I think we can approximate with something. Okay, let's say we are going to, since this first area here, let's say this is 1 by 1. Okay, let's say we know the area 1 by 1 here. So we need to know this part here, right? Which is going to be from the second one, okay? From the area 1/2 squared. Okay? So if we exclude the first rectangle, the picture shows that the all partial sum, the total of partial sums, is less than 1 plus okay, which is this is equal to. So we know for sure that the partial sums, this will be bound. Okay? So the partial sums will be bounded. And we know also the terms, the partial sums increasing, right? Because all the terms is positive. And we know that the partial sums, or we say, let me write with this, is converge if you remember the monotonic sequence. Monotonic sequence. So you know that this is increasing and it's bounded, and we know that it will be converged. And the series will be also be converged. And if you take the limit, okay, if you take the limit and take for this series, let me write again. This will less than 2, right? It's also less than 2. And by the way, if you want to know more about this summation here, this is the Euler. The Euler that found that the sum of this summations is pi squared over 6. But how to prove this is, I think, also difficult. Also difficult for me to prove. Okay, this is the first introductions. Okay, so you see that using the integrations, we can somehow estimate whether the series will converge or diverge. And perhaps to help you understand the problem, maybe you could imagine or visualize the chapter 7, the calculus 1, the improper integral. So if we can compute this improper integral and say, okay, this is converged, this is diverged, then we can also compute the series or estimate the series. So if the limit itself converges, the series will converge. If the limit is diverged, then the conclusion also diverges. Okay. So 1/x, we already did the harmonic series that it's diverged, then the sum also diverges. And if we take maybe another series, maybe 1 over square root of, let's say, square root of n, for example. Let me write here, just to give you some example. if you try to maybe put some numbers, okay, maybe some n equal 50, 100, or some other number as well, and take the partial sums, you will see the partial sums will lead to really huge number. And I think it's really like logically makes sense. It's square root, right? It will be a decimals on the bottom, and if it's getting larger and larger, the whole system will getting larger, right? So I think that's pretty logical. If we compare with this, if you see here, the denominator is getting larger, which means it's getting smaller, right? It's getting smaller when you increase n. It's getting smaller, and at some point, when you add something, it's not improved significantly, right? If you see this from the characteristics, okay? You will see that this characteristics makes the number getting larger, significant. Okay? But here, you add maybe 1/1000 squared. It's really small, right? So it doesn't really mean anything, or maybe just like really small fractions, right? Okay, so we can say that this is the whole point of my introductions. I think I can move this to here to make it easy to follow. Okay, so the integral test. Okay, so first we need to make sure the function, or the one that we need to integrate, we need to know that if this continuous function is a positive function, and it's decreasing function on 1 to infinity, and then let the sequence act as a function, and then the series will converge if the improper integral is converged. So the key is the improper integral. So you, you need to review that as well. So when this integration is converged, then the sum will converge. When this integration is diverged, then the sum will also diverge. But here's the thing. The sum will compute some value, right? In the integration test, we will not be able to compute that value. We just only show, okay, this is converged. But we are not able to compute. Unless we take the approximations method. Okay? Perhaps we can have some values. So we can only compute the integrations itself. Okay? And it's not the real summations of value. Okay. Because sometimes, maybe for the series, maybe we need to separate the series. Okay, maybe some of aspect can be taken as an integral, maybe some others maybe just as it is. So we are not capable on computing the exact value. And of course, since we are in this integral test, then if you remember in calculus 1, we have the p test, or p. We also have now a p series. We have also p series. This is for the sum. So this will be converge if we take these standards. So if p is greater than 1, and let's say diverge, if p less equal 1. So I need to make sure that we are understand the aspect. So what I'm trying to say as a conclusions, we can examine the convergence or divergence, but we are not taking this into equality between the sum and the integrations. Okay, this is difference. Okay, so the sum is not equal to the integral. I think we can also make this as an example. The sum of this is 5 squared over 6, while the integral is 1, the 1 over n squared. So that's also another point of view. The integral is our approach approximating using limit here. But the sum is, they are taking exactly that number. So what do I mean is, there is something missing here, right? So that's why it's not the same value. Also, if you change, maybe taking the trapezoid, there will be something missing. So it's not exact value. Okay. Okay, next is what we have as estimating the sum. This is just an overview. What can actually we can do for the integration test. If you want to make sure that we want to know the numbers, okay, we want to know the numbers. So perhaps approximation is one way. So we start with the notes that the Rn, the R is the remainder. Or we can say it's the error, okay, the error. So error when the Sn is used as approximation to the total sum. But if you understand what reminder is, I think it should be okay. So the smaller the error is, or the Rn, if we take this if we getting close to 0, then we are going to have a really good approximation or accuracy. So assuming, like this illustration, assuming that f is decreasing, let's say on some n, because n can be any number, to some number infinity, and we can compare area under y of x, or f of x, function of x. And we see that the remainder will be equal to that an plus 1, an plus 2, and it should be less equal to the integral computations. Okay? It should be below that, right? And if the approximation overestimate, then it will be reversibly greater than the integral. Do I have? Okay. Or if you have, we can also make this happen. It depends on the, do I have the picture? I think I forgot to put. So the second one is for the overestimate. Okay, just some illustrations. So basically, we are going to see the remainder is in between of two integrations. Okay. Okay, so if the R is the difference between the S and Sn, then we can take the integrations starting from n plus 1, which would be after that term, and from n. Okay? And the remainder is in between. Okay? Of course, all the aspect that the function needs to be continuous, positive, decreasing needs to be there, okay, to make sure that the integral test is working. So you need to make sure that the function or the sequence or the partial sums is going to be integrable. It's going to be integrable. If not, then we need to change the method. For simplicity, it's not really efficient in a way to determine the series. You need to, I think, if you see the formula and you know that, okay, I think I can integrate this, and sometimes that when integral test works. If not, then you need to change the method, change the test. But for sure, the first thing you can do is take the limit. If the limit doesn't exist, you can get this, okay, it's diverged. Or if the limit is not 0, it's also diverged. But if limit 0, then no conclusions. You need to take another method, okay? The main conclusion is converged, okay? So basically, how we are going to use this is we take some numbers and we check the numbers. Okay? So it's more like a computation method. Like we are doing a lot of numerics. So for example, because Rn is S minus Sn, so we need to maybe take some n, maybe n equal 10 for 10 terms. So we need to compute that first as a partial sum, okay. And then we need to take into this inequality and perhaps take some approximations and find how much error we want. Okay. And also another way to look at is we can also take the same inequality, but you could make it into so we plus this Rn with so if we plus this with Sn, okay, all the sides, then the Rn become S, okay? Because Rn is the subtraction between S and Sn. If we plus Sn, then it will become S, right? So this is also another way to write this is the same estimate. I think that's the integral test. Okay. Okay, now there is another test. Okay, we call the comparison test. Okay. So comparison test. Okay, I will bring the first theorem. Okay. And just to understand the concept, okay, what we are going to do in this test is we are just comparing the series. Okay. So for example, if we observe, consider okay, if we have this, it's the Zeno paradox as we know from the previous sections, and we know that this will going to be a geometric, right? It will be going geometrically, and it has the we can take the geometric sum like a over 1 minus r, right? If you remember, we take this as a 1 minus r. We can take that as our summation. So we can take this as our S, and we know that since this is going to be right here, this is 1 over 2 plus 1 over 2 squared plus and so forth, right? And we can make this into the sum. So 1 over 2 for the A, 1 minus the R ratio is 1 over 2. So it's going to be 1, right? And now consider the second statement, the sum. If we have the sum, another sum, that is going to be 1 over 2 with power of n, but plus 1. Okay. So if you see from this point of view, the series seems similar, right? And it's just adding some constant on the denominator, which means that this is going to be smaller, right? It's going to be smaller. So from this point of view, because we know the sum of the first one, then perhaps we can compare with the second one, and that's how this direct comparison will make the point. Okay. So due to this is going to be less than, and for sure for the fact this is going to be less than 1 over 2 with power of n, then for sure the series also affected by this nature. So this is less than sum. So the series is convergent by a direct comparison test. We're going to have a break. I think everyone finished looking at their score.
No, they make fun of the wall. You can jump over the wall.
Okay, so okay, let me just take some emphasis on this. So what we can do in direct comparison test is if you have like a series that is probably you can find method to find the convergence or divergence. One way to do it is find another series that's easy to compute, and you know it's convergent or divergent, and try to compare them. Okay? And for example, this is easy to look at, right? Okay. And my tips, and I think mostly in the lecture, I think only two possibility. Okay, only two possibility. So first is you can always take the P series to compare with, right? Like 1 over x with, like, let's say 1 over n with power of P, or we'll write bigger. This is for sure easy to compare, right? And the other series that might be useful is the geometric. Because we know that the R, we can make sure that R is less than 1, R greater equal 1. This is for converge, diverge, right? I think these two will be very common to be compared with. So if you have like unknown series, this is two series that you can pick. Okay, so first is the P series that you can easily look at and compute. And then the other one is the geometric. Okay? The geometric. And then the logic process on this comparison test is we need to know for example, we want to know the sum of this, okay? The 1 over 2 to the power of n plus 1, okay? And then we need to compare with 1 over 2 to the power of n. Okay? And then we compute this, and we know that this is converged to 1. Okay? So there will be 1 here. So it is impossible for the left side to be diverged, right? Because it's supposed to be finite to this 1, right? Because it's less than 1. That's how it works. So if this is going to be diverged, then this will be no conclusion, right? Okay. If this is, for example, this is just random numbers. Okay. So if this is diverged and this last is still applicable, this will be no conclusion. We are not sure yet it's converged or diverged. That's why, look at this, okay? These two very, very important aspects in this comparison, okay? So if your Bn, which means this one here, if this is divergent, then we need to show the counterpart, okay? So the An need to be greater than Bn, so that we can conclude that An will be diverged. Okay? So if something smaller than An is diverged, then the sum will be diverged as well. Okay? I hope that makes pretty sounds and logical, right? Okay. But there is something something terrible happen. So if we take, for example, 1 over 2n, and it's not plus 1, it's minus 1. What do you think? What do you think? Okay, so first maybe we try to take the inequality. So we take this. Okay. If this is plus, then this will be smaller, right? If this is minus, what will happen? Well, just take some numbers, maybe 3 is 8, this is 7, right? So this is larger, right? So this happens, right? So this is how the problem with the comparison task. So we need another approach. So we're going to use the regular comparison task. So what we are going to do is we are going to develop a new task that we call the limit comparison task. Okay, okay, so we are going to suppose that an and bn, they are series with positive terms. And then if we are going to take the limit of these two sequences, ratios, an over bn, it will be concluded as a finite number, as a constant. Of course, c need to be positive if we want to make them. So there will be some conclusion here. Okay. C will, if c is positive, okay, then the series an and bn can be both convergent or divergent. It depends on the bn. Let me show you how. Okay, so let's say we are going to conclude the series here. Okay, so let's say we are going to take the series. We want to take this series here, 2 with power n minus 1. Okay, let's say, suppose we are going to take some an as, of course, the unknown one, okay? And bn is, let's say, our known series, okay, which are the p series, right? Or it's geometric, sorry, not p series, it's geometric series. Okay, now we take the limit. As we approach this with the limit comparison test and take the an over bn, and this will be 1 over to the power of n minus 1, and this over 1 over to the power of n. And we are going to have, oh, I forgot the limit, sorry. We need to write the limit here as well. So this is going to be 2 with power of n over 2 to the power of n minus 1. Okay, and then we solve this with the limit property. We divide by 2 with power of n, divide by 2 with power of n. This is 1, 1, and this will be 0 by limit, right? Okay. So we take this, and I think I will write step by step. So this is 1. This is 1. Okay, so we can conclude that this is equal to 1. So what can we take conclusion from here? Okay. This is the same conclusion with this, right? It's positive number 1. Okay. Since bn is convergent, then this one also convergent. That's how we read this conclusions. So both series converge or both diverge. So it can be both. It depends on bn. Okay. So since let me write here. So since we know that this series converge, then by limit comparison test, this limit is also converged. And perhaps you can also take notes that, as I mentioned, mostly comparison will work on if we compare with the P series or if we compare with the geometric series. Okay? I think you can focus on those two as the priority. Okay, any questions? Any questions on this? Okay, let me put one example, just one example here. So determine the series. Converge or diverge. Okay. It's intimidating, right? Seems like really huge, like a monster. But of course, we're still in a limit comparison test. So perhaps this is going to be comparable with something, right? And limit comparison test is actually like it works for most of the series that is comparable with. So I think instead of just like taking the direct comparison test, you can just focus on this limit comparison test. It works perfectly. Because sometimes in direct comparison test you have some weakness, right? Like if you are maybe like in the previous one, we changed a little bit the numbers and it's not worked right. But here, it's worked for every comparable series. So what's the key here? What's the key? What's the idea?
I believe that we can just find a series which consists of either numerator or denominator of this series, and then just find where they
Fine, yes, sure. So if we take we say, what's the highest power? We say that this one, right? This one, and this one, right? I mean, in terms of the fraction itself, that one is the dominant part, right? So what we can do is, let's say we are going to imagine that, or maybe we take the a. Let's say an is that part, so 2n squared plus 3n, okay, and then over square root, and then 5 plus n to the power 5, right? And then let's imagine we have a bn that is going to be 2n squared and n and then with 5/2, right? The power of 5/2. And again, with the limit comparison test, we are not really comparing this. We just take these two as comparable to the formulations. Okay. So we can take the limit comparison test directly. Okay. But the problem will happen if the limit is 0 or negative. So that may be some problem, or maybe you need to change the method. So take the 2n squared plus 3n but of course you need to have a good algebra for solving this problem. Or maybe let me simplify this first. This can be simplified. Two divided by n squared, so half, right? So we can write this just 2 over square root of n, or 2 divided by n with power of half. Then multiply. Okay. I think it seems like big, but it's actually just a basic algebra, right? The algebra requires you to be patient and see the moment, see the pattern. Actually, doing algebra like in your leisure time is sometimes helping you to focus. But if you feel like you're getting like distractions a lot, then maybe that's not a good way. 3 and 1 2 oh 3/2, right? And then 2 then solve using the limit concept. So we divide with 2.5 is the highest order, so we divide with the n with power of 5/2. So this will be 2 plus divided by n I just ignore the red color, okay? Just try to make sure that it's okay. So 3 minus 1, right? Minus 1 is supposed to be over n. And then 2. And then this will be 5 over n with power 5 plus 1. And then you can ignore the one with variable, right? Because that's will be 0. So we could say that this is going to be just 2, right? Just 2. 2 by 2, so it's 1. Let me write here. So this will be equal to 1. But what's the conclusions? We solve the limit, but then we need to make a conclusions. Okay? Now, because we are taking the bn is 1 over n with power of half, which in the p series, it's less than 1. The p is less than 1, which means it's diverged. So whenever we find a positive number here, then the an will have the same consequence as the bn. So if the bn here is diverged, then the an will also diverge. Okay? So this will, which means the I think I will write here. I don't have space. Let me resize a little bit. So since we know that this is diverge, then series I will just write an too long is diverge. I mean the an, the same an that's the beginning, is diverge by a limit comparison test. So the focus for the chapter is, I think, is this part here. This is limit process in calculus 1, right? And some algebra, right? So yeah, I need to be honest with you. Like, if you are still having difficulty in some algebra, or maybe utilize some calculus 1 formula, like compute limit, derivatives, integrations. Calculus 2 is very, it's not as like some other course in other lecture. Maybe they will define like, okay, this is separate materials. But in calculus 2, we are not really that separated. We are still taking some parts of calculus 1 in calculus 2. So that's why it's, I believe, the difficulty is because of the content. If this is like a totally separate material, like the content is really separate, maybe it will be a different case. Okay, that's what I think you need to aware.
Over and square root of
This one.
so that is 2.
Yeah, it's the same thing. Same thing, right? Same conclusion, I mean. I want to end this course with just a little bit intro for the next week, which is the alternating series. Okay, consider harmonic series. We know that the harmonic series is diverged, right? It starts with 1 plus half plus 1 over 3 plus 1 over 4 and so on and so forth. And we conclude that, as we mentioned before, it's diverged. Now, what will happen if we have this? If you have these two series, okay, in which if we see the first one is actually the harmonic, but with a twist that it has an alternating sign. And the other is also similar to the harmonic, but it has the n over n plus 1, and then it has the alternating sign. Okay. If you think closely and see how the change in the line numbers, okay? If we take the line numbers, or if you take the graphs, okay, if you take the graphs, and let's say we have 1, 2, 3, 4, 5, 6, let's say 6. If we take 1, let's say 1 is here, and half is, let's say, here. Okay. Let's say we have here, right? In a normal harmonic, we are going to have this, and then we still have, like, in a good way, right? But if we take the alternating series, then we are going to have the negative counterpart, okay? And then if you see, when we increase 1 over 3 maybe around here. So this is 1, 2, 3, and 4 maybe around here. And we see if we increase more and more, how it looks like. So it's going here. It's going to, okay, perhaps it's going to be near one value. And now we could think if we want to make some summations. Let me put here. Okay. So if we have this alternating series, and we know that for sure that it is decreasing. Yeah, it's decreasing the terms. Is less equal to the previous terms, and limit is equal to 0, as we see from the picture. Then we could make this as a convergent. We are going to take more discussion this next week. Okay. We have left, okay, and perhaps this picture can help you to look at. Okay, and we are going to have a more discussion on this next week. Okay, we'll just stop until here. Any questions? Any questions? Did you find any filters or no? Or no need?
No need.
No need? Okay. I think some students need, but I'm not sure. they want or not. That's up to you. I mean, I'm just give you some suggestions to take some tutors. Like if you really want like tutoring periodically, like maybe every week or every 2 weeks, and you need to think about that. You need to think about that. Remember, I already taught this at the beginning of the course. So, and I believe you are an adult now, so you need to take responsibility for yourself. So I think I will end my course until this part. Again, we still have a long journey in Calculus 2. We haven't got into the main course. This is like just intro. The main course is like at the end, actually, the 2 chapters at the end. So hopefully we can have enjoyable main course. Okay. I know that maybe some of you think maybe this is not really your likings, and that is true for most cases. But some logic part or some reasoning in some chapters, I think you need that, especially for engineering. You need that for sure. You need that. Okay. So I will end this with as usual, the feedbacks. Short questions. Just I think
I don't trust you.
two questions. Two or three. Very short questions. Oh? Okay.
2 seconds.
Okay. Okay, I think we can start. Okay, how do you feel today? Sleepy? Sleepy? After lunch, hot today, and then you got into the class. Air conditioner is good, right? And if the weather is hot and the air conditioner is good, you are thermodynamically stable. Which means you prefer your stable position, which is sleep, right? Like your Wednesday course. This is how you understand thermodynamics. The particles can move, or material will move when they are energetically stable.
What is Travis?
Oh, some words, Japanese words. Okay. Oh, Jason sing. Okay. All right. Demotivated. Oh, why? Okay. Okay, I think we can start. Issues. Why? Why? Maybe you're correct. Maybe this is like the universe is telling you that we need to just close the lecture. Okay, anyway, I think I will just end the lecture on here, okay? We are going to save this next week, okay? Okay, see you next week.